Hello and welcome to the first in a number of presentations about the moon. The moon is a body we're all familiar with in a way. We've all seen it in the sky. It's the brightest thing in the night sky and the second brightest thing in the sky after the sun. I suppose most people obviously know that it changes shape throughout the weeks. Most people know it affects the tides and that we've walked on it. But for an object that is so familiar to us, most people know very little about the moon, and that's what we're going to try and address in these presentations here. And the first presentation is called the Earth's Companion, the Moon. It's a basic introduction to the size, distance, and other basic properties about the moon. So, I suppose, the best place to start with is size. How big is the moon? Well, as we can see here, the average diameter of the moon is a little under 3,500 kilometers. Now, it's hard to imagine what 3,500 kilometers look like. So to help us, I've plonked the island of Ireland onto the moon. And even though the moon, as we will see, is relatively small compared to the Earth, it makes Ireland look fairly small. So it's a big rock. So it's a big body that is orbiting our Earth. Another way to look at size is how does it compare with the other bodies in the solar system? Well, if we first take the Sun and the 8 planets plus the minor planet Pluto, we can see that the Sun is just under 1.4 million kilometers in diameter. In fact, 99% of all the material in the solar system is in the Sun, and the remaining 1% is what makes up the planets, the moons, asteroids, comets, everything else. So it's a massive body. But Jupiter, Saturn, Uranus and Neptune are fairly big planets as well. Then we have the smaller Earth, Venus, Mars and Mercury. And then, as I said, the minor planet Pluto. So how do the moons in the solar system, or at least the larger moons, compare, and our own moon, compare to these sizes? Well, as you can see, Ganymede, the largest of Jupiter's moons, it's only slightly smaller than Mars, and it's actually bigger than the planet Mercury. So moons, not all moons are smaller than planets. What defines a moon is that does it orbit a primary planet. And we can see here that our own moon is the 5th largest moon in the solar system, and it's the 15th largest body in the solar system. So it's an important part of the solar system family. After this, I suppose the next most important thing that we want to know is distance. So how far away is the moon from us? Well, first of all, if we look at the moon and the Earth side by side, you can see how small the moon does appear. But if we were to reduce their sizes so that the distance between them was to the same proportion, this is how they would appear. And that distance is an average distance of a little under 385,000 kilometers. Now, in fact, this is quite a good representation, and I can prove it, in that this is a photograph that was taken by NASA's probe OSIRIS-REx. And you can see here in one photograph, it's a beautiful image, the Earth and the moon in that one photograph. Now, they look a little bit closer there compared to my diagram, but the image is taken at a slight angle, so they just appear closer. Again, it's hard to imagine what 385,000 kilometers is, or how long is that really? Well, let's say we were able to build a road, a straight road between the Earth and the moon. We couldn't, but listen, we're just using our imagination, and this is going to help you to understand the distance. So let's say there is this road, and we get in a car, and we drive that car at 100 kilometers an hour. Now that's the speed limit of the national roads. It's about 60 miles an hour. Now if we were to drive that car non-stop day and night, 24 hours a day, 7 days a week, how long would it be before we would get to the moon? Well, the answer is about June 10th. So you'd be driving for over 5 months non-stop at the speed limit to get to the moon. Now, on a universal and even solar system scale, the moon is very close to us, but it's still quite a distance. And that distance actually is expanding a little bit because every year the moon drifts about 4 centimeters further away from us. Now, 4 centimeters seems very small when you're talking about hundreds of thousands of kilometers. But if you multiply that by billions of years, it means that into the future, the moon will be much further away. And if we go back in time, the moon was actually much closer and appeared far bigger in the sky than it does now. The next main issue about the moon is its phases. So we know that in any given night, the moon can appear quite different in the sky. It ranges from being a dark disk that we can barely see, or not see at all, to a semicircular shape of light. And then a few days later, it's a full bright disk, then another semicircle of light, and then it goes back to being dark again. So to explain this, let's say we are looking at the sun, the earth, and the moon. Now, in this diagram, we're looking down on the planet Earth and the moon. So we're looking down in the North Pole, so to speak. And the moon is orbiting around. Now, when the moon is between the Earth and the sun, now the distance between the Earth, the sun, and the moon in this diagram is not to scale at all. The sun is 93 million miles away. So this is just to kind of show you how the phases work. But you will see that when the moon is between the Earth and the sun, the side of the moon that's facing the sun is lit up, obviously, which means that the side that's facing Earth is in darkness. So that's why we see it as a dark disk, or we can barely see it in the sky. And we call this the new moon. Then, when the Earth orbits around the Earth, it reaches a point where we can see half the lit side and half the dark side. And so it looks like this semicircular. And we call this the first quarter. And then as the moon progresses round the Earth is now between the sun and the moon. And the side of the moon that's facing the sun, and therefore the side that's bright, is also facing the Earth. And therefore we see the moon as a full bright disk. And this we call the new moon. And a few days later, it gets into a position where again we see half the bright side and half the dark side, and it looks like this semicircular, and we call this the third quarter. So this explains why the moon changes in shape as it goes around the Earth. Now, the moon does orbit the Earth, but if we were to get really technical about it, it's actually the Earth and the moon go around a common point. And this point is called the barycenter. Now, this center is actually in the Earth, so it's not in the middle. So it isn't that the moon is going around the center of the Earth. The Earth and the moon are going around a point it's about 1,600 kilometers below the Earth's surface, about 1,000 miles below the Earth's surface. So if we were actually looking at how they orbit with respect to each other, it would look like this. As you can see, the Earth is going around that point, as is the moon. Now, you've heard me mention the distance between the Earth and the moon as being an average distance, and this is because the distance between the Earth and the moon changes day in, day out. And the reason is that the moon doesn't go around the Earth in a circle, but rather in an ellipse. Now, an ellipse, as you can see here, is like a circle, but it's slightly squished. So it's more like an egg shape, not quite an egg shape because both ends are the same. But so with the squished circle. Now, not using a very scientific term, but the squishiness of the circle here is exaggerated. The orbit is closer to a circle than this diagram here would indicate, but I just wanted to show you what an ellipse was and make it quite clear. But it means then that there's a point on the orbit when the moon is closer to the Earth, and a point when it's further from the Earth. So when it's the point when it's furthest from the Earth, we call this the point of apogee. And this point is about 405,000 kilometers, and that point actually varies from month to month. And the point that it's at its closest, we call it the point of perigee. And that varies around 365,000 kilometers. Now, when the moon is actually closer to us, it appears bigger in the sky and brighter in the sky. We don't really notice because it isn't like you can take the moon when it's at its furthest point and compare it directly when it's at its closest in the sky, because there's only one moon, so you can't do that. But if you took a picture of the moon when it's at its furthest point and when it's its closest point, you would actually see that when we compare the two, when it's closest to us, it's 14% bigger and it's 30% brighter. So maybe after some of my later talks, you might be able to do some photography and look at the moon at those two different points. The next thing we're going to look at is lunar weight. Now, this might seem an unusual thing to look at, but in future presentations, you'll see how the weight of the moon, and especially the weight of the moon relative to the Earth, is actually an important feature. So how heavy is the moon? Well, it's 81 quintillion tons. That's 81 followed by 18 zeros tons, which is very heavy. But you know, who can imagine what 18 quintillion tons is? So let's say we were to get a balance, the biggest balance you could imagine. And we put the Earth on one side. In order for it to balance, we would need to put 81 and a half moons on the other side. So the Earth is the same weight as 81 and a half moons. So we can see that the moon is quite light, because it's small, compared to the Earth. Now, this also has another effect. As you know, gravity keeps us on the ground. And so there's a pull. It's like the Earth is pulling on us and keeping us to the ground. Now, the bigger a body is, the greater that pull is. So the gravity is more powerful. And the smaller the body, the weaker the pull is. And that means that the moon's gravity is only 1/6 of what it is on Earth. And that means that if someone weighed 120 kilograms on Earth, they would only weigh 20 kilograms on the moon. Now, this is meant to be a funny cartoon here. You would look the exact same because you're the same mass, but just that mass would weigh 6 times less because the gravity is pulling you less. And that's why when you see pictures of astronauts walking on the moon, they seem to bounce. That's because they're 6 times lighter. So when they walk, they're leaping up because it's easy for them to do that because they feel 6 times lighter. Another interesting aspect of the moon is its temperatures. Now, the one Earth month is the same length as one lunar day. So a day on the moon lasts a whole month in Earth time. We'll discuss this in another presentation because this is basically because the moon rotates around the Earth at the same speed as it spins around its axis. So therefore the same face of the moon is seen from Earth the whole time. But one of the effects of that is that it means that each spot on the moon spends 2 weeks in constant sunlight. And 2 weeks in constant darkness. So that means it can get very warm and very cold. And added to that, the moon has no atmosphere because, as we said previously, the gravity is very weak. So it can't hold on to the air. So there's no air atmosphere around the moon. And an atmosphere acts like an insulation blanket on a planet or on any space body. And what that does is that it protects the body from the worst effects of heat from the sun, but also it prevents a lot of heat leaving the body at night when the sun isn't shining. So it can maintain, it can control the temperature. So with these two facts, a long day and no atmosphere, it means that temperatures on the moon are very extreme. In fact, the hottest temperature that's reached on the moon is 134 degrees Celsius. Now, water boils in your kettle at 100 degrees Celsius, so it's even hotter than that during the day on the moon. And at night, it can get to as low as minus 154 degrees Celsius. The freezer at home is only minus 20, so minus 154 is freezing. And as we'll see in a later talk about the Apollo missions, we have to plan for that when people are walking on the moon, when they're living on the moon, and hopefully in the future when we set up a base on the moon, we have to take into consideration that it's going to be roasting or freezing and take account of that. Now, where did the moon come from? And this is something which is very contentious because we don't know for certain. We have to become detectives in a way. What we do is we start looking at evidence. We look at what's the makeup of the moon, how does it move, its age, and a whole lot of other factors. And we take them all into account and we come up with a theory as to how the moon might have been produced based on what we know. But as we learn more, that theory may change. So at the moment, the most accepted theory is that called the giant impact hypothesis. Now it sounds like a fancy name, but really what it is that 4.5 billion years ago, so that's 4.5 with 9 zeros after it, so a long time ago, about 500 million years, or about 500 million years after the initial Earth had formed, we had what is known as the proto-Earth. Now, how planets formed and how the sun formed was that originally you had this large cloud of particles and pieces that may have been formed from the death of an earlier star. And gravity started to bring these pieces together and they formed clumps, and then clumps joined to form bigger lumps, and they grew as their gravity grew. And then you had these large planet bodies, and you had many of them, far more than we had today. And their paths crossed, so these would be banging and crashing into each other. So the theory is that 4.5 billion years ago, we had this proto-Earth and a Mars-sized type planet, and which has been called Theia. And these two bodies collided. Now, when they collided, they didn't break apart and float away. What they did was they kind of merged in together to form a bigger body, the Earth we know today. But in the process, a small bit of the mass of the two bodies was thrown off into space. Now, this ejected material didn't fly away. What it did was it was held by the gravity of the new Earth, and it went into orbit and it formed a ring around the reconstituted Earth, like the ring of Saturn, and that's kind of what it looked like. It would have been a ring around the planet Earth. But over a long period of time, the particles in this ring started to link up and join and form clumps and lumps and grew till eventually it formed the moon. And that is how we believe the moon came to be our companion orbiting us. Now, what can you see of the moon when you look up into the sky? Most people think it's just this blurry grey piece and there's nothing really to see except a shiny disk. But you do know that there are little blotches on the moon. If you look carefully at it, you can see that there are certain blotches. And if you look at the moon often, and especially frequently when it's the full moon, you'll notice that these blotches are always the same. So you can start identifying, these pieces, they're always there. And some say that it looks like two large eyes and a mouth, and that's why they say there's the man in the moon. But if we were to look at this a little bit closer, these dark patches are called seas, or the Latin is mare. Now, they're not seas like they are on Earth because there's no water on the surface of the moon. It's quite a dry a body. Now, we do know that there's water under the surface, and we'll talk more about that in a future talk. But hundreds of years ago, they thought that these dark areas may have been seas, and therefore they called them seas, or as I said in Latin, mare, and the name kind of stuck. So we have the seas of rain, vapors, islands, storms. Here's a really strange name, the sea that has become known. I wonder what they were thinking when they named that particular sea. We have the sea of moisture, the sea of clouds, nectar, fertility, tranquility, which I think is a lovely name. And it's also, this is the sea or the area where Apollo 11, the eagle of Apollo 11, the eagle lander, landed, and where we first walked on the moon. You have the sea of crisis, serenity, and of cold. Now, the moon is covered in thousands of craters, but we can't see these with the naked eye. Some of them, if it's a good night and a clear night, you might be able to make out. So there's the Grimaldi crater, the Copernicus crater, and the Tycho crater. If you've got good eyesight, it's a clear night, you might be able to make them out. Now, you'll find it difficult when you first look at the moon to see all these different distinct patches. But the more you get familiar with it, you might surprise yourself how much detail you can actually make out. But of course, the more we get to know the moon, we'd like to look at it through a telescope. And seeing the moon through a telescope is a beautiful sight. And we'll have a special presentation on looking at the moon through a telescope later. But a little warning about telescopes. Now, in carpentry, we have two sets of tools here. Now, you know that the top ones here are equipment and the bottom ones are toys. It's so obvious it seems silly to make the difference between them. And no one is going to use toys to make a real cabinet or a table or a coffee table or whatever. That's obvious. The problem is that in astronomy, in many shops, it can be difficult to know the difference between telescopes that are toys and telescopes that are equipment. Because unfortunately, some shops will sell toy telescopes and say that they're really telescopes you can use to look at the moon and other objects, when really they're not. But how can we tell the difference? Well, if a telescope on the box just talks about magnification and how big it'll make things, be wary, because really magnification, though it's important in a telescope, it's not the first feature you look for. Because what's very important is before a telescope can magnify an image, you want to have a good quality image coming into the telescope. So things like the objective lens size, the quality of the lens, and the light capture ability. And you'll see a lot of good telescopes will have these kind of descriptions on them. And this is because if you're getting a very good image, bright image into a telescope, then you'll be able to magnify it with the eyepiece and see something that's worth looking at. Whereas in these toy telescopes, no matter how much you magnify the image that comes in, it's just blurry and bad quality. Another important feature is sturdiness. Now, usually when we think of the telescope, we just think of the main telescope part. But the bit that it stands on, usually the tripod, that's just as important to have a good quality tripod, because If the tripod is cheap and weak, every time you go near it, it'll wobble and shake. So when you're looking through it, everything is is kind of hazy and fuzzy, and it's useless. So always check that the telescope has a good sturdy stand, that, if you just lightly touch it, it doesn't wobble away. Because you'll notice in a lot of the toy telescopes, as soon as you just touch it, they wobble, they're cheap and they're plastic. Also, if a telescope is under €80, it's not really a quality telescope. It's more of a toy than an instrument. You should be really spending a minimum of 100 to €200 for a starter level telescope. Now, that might seem a lot of money, but really when you compare it to, the PlayStation and some other objects which are much more expensive, it's actually great value, because you will get years of joy out of a good telescope. So, that said, just a few tips on using the telescope. When we were talking about the moon and the naked eye, we were really intrigued with the full moon, because we said we could see all the features on the moon with the naked eye. But with a telescope, actually the full moon is quite boring, because the sun is shining right down on top of it. So everything is bright and it looks very flat and there's no shadows. So it's hard to see details, very hard to see craters. So what we really like is for the moon to be in phase. And in phase means that part of it is dark and part of it is bright. And the region that we want to look at is just that region near the dark side. And this is what we call the Terminator. And along the Terminator, the shadows are at their greatest. And therefore you can see, it's like, you can imagine a very faint drawing, and then you take a dark pen and you draw around all the features with a dark pen, and you can see them much more clearly. Well, that's what shadows do to the features. So I've taken a photograph here of an area along the Terminator in this moon. And you can see that the craters are very distinct, because the shadows show up and it looks quite pockmarked. So you can see the lovely detail on the surface of the moon. And here, for instance, are a chain of 4 very nice craters, and they vary in size from the smallest being Herschel at 41 kilometers wide to the largest, Ptolemaios, at 153 kilometers wide. So that's about as wide as Ireland. So these are quite large. And craters were formed when meteors struck the surface of the moon and dented it in. In fact, it's a huge force, and you might notice that in some of the craters there seems to be like a little point. Well, they're more than just little points. Like in the central peak in the lower crater there is 1.5 kilometers. It's nearly a mile high, this peak. And how that peak formed was that when the meteor hit the moon's surface, it was with such energy and such heat that it actually turned the stone to molten rock. It liquefied the rock. And when you throw a stone into water, it goes in and then the water kind of bounces up and then flattens out. Well, the same thing happens when the meteorite pulverizes, liquidizes the surface of the moon. You get this bulging up of the liquefied rock, but unlike the water, where the water just flattens down again, the rock actually cools before it can flatten down, and so you get this peak. And with the telescope, you can see these little peaks. So it's amazing the detail that you can see on the moon with even a simple, small telescope. And just to further illustrate the point, here are a number of photographs I took of the moon at different phases. Day 6, day 9, day 10, and day 12. So day 0 would be the new moon, so 6, 9, 10, and 12. And you'll see there that it's the area that's closest to the dark part of the moon that's most detailed. And as you move away from the Terminator there, you'll see that the moon tends to get flatter and more featureless. So that's really it. That's your basic introduction to the moon. I hope you enjoyed it. I hope you found it informative. In future talks, we will go into greater detail about lunar eclipses. As I said, what you can see with a telescope. We'll talk about the Apollo missions of the past and the Artemis missions that will take us back to the moon by perhaps 2025. In the meantime, you can get much more detail on the website, themoon.ie. I have some activity sheets and information sheets, some more videos, and there's even a test, a quiz that you can take part in just to see if you're paying attention. So there's much more to follow. Do check in to see when I post a new presentation. But until then, I wish you clear skies.